In this lesson, we'll continue our exploration of acids and bases, looking at the needs of high school students. Today we're going to look at acid-base titration and the stoichiometry that goes along with it. All right, last week we talked about the definition of different categories for defining what acid and bases are. We said there's an Arrhenius acid-base theory. We said there's a Bronsted-Lowry acid-base theory. And we said there is a Lewis acid-base theory. Now, in this class, we don't do a lot with Lewis acid-base theory. The only thing I want you to need you to know about Lewis acid-base theory is basically what it is and how to demonstrate it. Okay. So for an Arrhenius acid-base, we said that acids are defined as those chemical species that give away hydrogen ions to water. Okay, so an example of that would be the weak acid dissociation that we used in our first lab in this unit, where we tried to neutralize a weak and a strong acid. Okay, so this is the acetic acid. We're working with vinegar, and in Arrhenius, an acid donates a hydrogen ion to water. And when it does that, we also have the acetate ion left over. Okay, something that we don't get into in entry-level chemistry, but you do get into in college chemistry or AP chemistry, is what you use all that for, as far as figuring out what the concentrations are. We said that the math that we did last week, and we did as homework, you can calculate the concentration of the pH directly. But with weak acids, you can't do that. You have to have more math to be able to do that, okay? And so that's where you get something called an acid ionization constant. We don't have to do the math here, but I just wanted to show you that what you do is you take the hydrogen ion molar concentration and you multiply it times the acetate or the anion. In this case, acetate is the anion, its concentration, and put it over the concentration of the acid itself. Now, you usually know what this is, so you know what this bottom number is. You can look up the Ka. What you don't know is what the hydrogen ion or acetate ion or whatever the acid anion is. You don't know what those are. Okay? So this equation helps you to calculate that. What we did go over last week is whatever the concentration of the hydrogen ion is also the concentration of the anion. Remember that? Yeah. Okay? So that being the case, you could treat this like x and this like x, and so you have x squared on the top. And so you have a Ka value, you have a concentration value, initial concentration, the amount you actually put into the water or the solution, and then x squared. And then you have to use the, let's see, what is that called? What is that equation where you, quadratic equation. Okay, you can use that, or lucky for you guys, if you have a better quality calculator, there's a solver button on your calculators nowadays. Okay? Yep. When I was going to college and doing all this, I had to convince my professor it was okay to use the solver button because he wanted us to use the quadratic equation. So I memorized the quadratic equation. I learned to use it. I rememorized it. I guess I knew it at one time. And, I saw I could solve the problems both ways, which is not a bad thing. But if you go to college and do these kind of calculations, if you're doing this in AP chemistry, you're going to want to know how to use that solver function on your calculator if you've got a good quality calculator, okay? Now, that's the Arrhenius acid dissociation. Now, the corresponding base definition for Arrhenius. Arrhenius base is a chemical species that donates hydroxide ions to water, okay? So an acid is any chemical species that donates a hydrogen ion, and a base is anything that donates a hydroxide ion in the Arrhenius acid-base definitions. Then we introduced on Friday the Bronsted-Lowry system. And in Bronsted-Lowry, an acid is anything that donates a proton to a covalent bond with another species. So this hydrogen here on this acid is giving this hydrogen to the water, forming a covalent bond to form hydronium. The name of this is hydronium, okay? And that still leaves us with our acetate ion by itself. Now, here's a new set of terms for you. This is the acid because it donated the proton. The base in the Bronsted-Lowry system is the chemical species that accepts the proton. Okay, so in Bronsted-Lowry, the acid donates the proton to a covalent bond with another species. The base accepts the proton in a covalent bond from that other species. Okay, so if this is the acid, then it gives away the hydrogen. This is the base that accepts the hydrogen. The resulting formation here from the base, when we put that hydrogen on the water, in this case, now it could be anything. It doesn't have to be water. Any chemical species that accepts that proton, this becomes an acid. Okay, this hydrogen ion can be given away to push this equation back the other way. Okay, this is a reversible reaction in this case because I got a weak acid. Okay, and so since this is it gives away a proton, or is capable of giving away a proton, this is also an acid. But we call it the conjugate acid of this base. So this is an acid because it can give away a proton to something else. In this case, it can give that acid, that hydrogen, back to this acetate ion. But since it was built from building or putting a hydrogen ion in a covalent bond on this water, it's an acid that we call a conjugate acid of this base. And this is the conjugate base of this acid because it will accept the proton that comes from this acid to reform acetic acid. Okay? So that's the system that we call Bronsted-Lowry. Okay? Bronsted-Lowry. And Bronsted is spelled with this funny looking O here because they have an O that looks like that. I guess you could call it an O. It probably has a different name, but he was Danish. Okay? Lowry is British. Bronsted was Danish. They just happened to come up with the same acid-base theory at about the same time, so they're both given names for it. Now, if we write an acid dissociation constant for this, we're going to leave out the water because whenever you have any kind of a constant like this, whether it's this constant or any other constant, the species of chemicals has to be the same physical state. And water is not the same physical state as these others. Okay? So water is not part of the Ka, and basically it's the same equation. An equilibrium can't be calculated when something is in a different physical state. You don't have the same concentration. The concentration is basically doesn't make any sense when you're talking about liquid water and liquid water. It's like a useless unit anyway. There's a lot of reasons why we don't include it, but for me at least, the way that I like to think about it is the primary reason it's not in the same physical state. That then fits when you do concentration or equilibrium constants for gas phase or something else, okay, where you have to also look at only what's in the same physical state or phase. All right? And then we also talked about the Lewis definition, and in the Lewis definition, we're not going to do any math with it, but in the Lewis definition, it's all about the electron. So remember Lewis dots, the Lewis structures, Lewis formulas, you had those electron dots, okay? So the hydrogen ion from the acid, this is just a general formula for any acid. A stands for any anion for any acid. The hydrogen ion comes off and then covalently bonds to a pair of electrons, all right, in another chemical species. So that kind of fits this Bronsted-Lowry theory. But in a minute I'll tell you there's more to it than that. So the definition that Lewis gave for an acid is any chemical species that accepts a pair of electrons in a covalent bond. All right? So this hydrogen from this acid species accepts that pair of electrons in a covalent bond from another species. So this is all about donating protons. This is about accepting electrons. Okay? The base is the species that provides the pair of electrons for the covalent bond when something else, when another chemical species bonds with it. So why different definitions? Well, This is a very limited definition, and there are some acids and bases that would not be defined as acids and bases in the Arrhenius system. Okay, so for instance, ammonia is a very common base, but in the Arrhenius definition, ammonia is not a base, but it behaves like a base. It does all the same stuff as a base. There's some reasons why we won't get into right now, but ammonia would be defined as a base in the Bronsted-Lowry system. Okay? Then why bother with Lewis? Well, here's the thing. There are some salts, chemical species that don't have hydrogens in them that behave like acids. They do all the same work as an acid. They change the pH like an acid, but they would not be defined as an acid in the Bronsted-Lowry or Arrhenius system. But they would be defined as an acid in the Lewis system. So what we're trying to do, I say we, chemists, the body of chemists, chemistry is a field of study. What we're trying to do is define things by their behavior. Okay, it's about the behavior. That's what we talk about models in here. When we say a model, it's about trying to figure out why something behaves the way it behaves, the cause for behavior. Well, Arrhenius was trying to define behavior, but his definition was limited. Bronsted-Lowry tried to define behavior or figure out why behavior occurred, but it was limited. Lewis came up with a much more ubiquitous definition. That is to say, it has much more, not ubiquitous, because that means it's used a lot. Probably Arrhenius is more ubiquitous, but it has a broader application. Okay, so of all the definitions, Lewis has the broadest possible applications, but it's the most difficult to work with. So that's why we have these different definitions. Okay. In acid-base theory, we probably work with Bronsted-Lowry more than anything else. But day-to-day, Arrhenius is how we think about things, because it's just simpler. Okay? All right. So that's just kind of the overview about those three different definitions and systems of understanding acids and bases. Now, in all of our acid-base discussions last week, we were talking about strong monoprotic acids, and we did do it with one weak monoprotic acid. Now we need to talk a little about polyprotic acids, okay? Polyprotic acids. So what that means is there's more than one hydrogen that can be removed. Because when a hydrogen ion is removed from an acid, what we have is actually a proton. So polyprotic acids, okay? Now there are a lot of polyprotic acids. There is only one strong polyprotic acid, and that's a diprotic acid called sulfuric acid. It's the only strong polyprotic acid that you need to know. Remember that I gave you a list of, 7 strong acids, and the way you define, or whether you can figure out if it's a weak acid is, if it ain't on that list, it's weak, okay? So you just need to memorize the 7 strong acids, and I have a little trick for figuring that out. I'll try to tell you this week when we get to it, where you don't have to memorize as much, but you may or may not like that. You might like to memorize, I don't know. So this is the only strong polyprotic acid you need to know. So this acid, sulfuric acid, is strong, but only for the first proton removed. All right, so remember, a strong acid is defined as a strong acid because it dissociates completely. It completely deprotonates. Dissociation of an acid and deprotonation for an acid is the same thing. It means removing a hydrogen ion. So here's sulfuric acid. And using the Bronsted-Lowry system then, here's water. We're going to simply dissociate, deprotonate. And so what's going to happen is a single hydrogen, just the first proton, is going to be removed here for the strong acid. Okay? The result then is that we get hydronium and bisulfate or hydrogen sulfate. It can be called either one. But this is the strong acid. This is the one where the hydrogen dissociates completely. Okay? This hydrogen here, this second hydrogen, can also be removed. It can also be deprotonated, but that deprotonization is not strong. It doesn't happen completely. So we have a second equation for this second deprotonization or dissociation or ionization. And now we have the sulfate ion in solution. So because this is weak, we actually have a reversible reaction. And we have an acid ionization. There's actually a constant for both, but this one's not much help for most things. This one helps a lot. Okay? In that first lab we did in this unit, where we looked at the behavior of a strong monoprotic acid and a weak monoprotic acid, we were looking at the strong acid starting at about pH 2.4, so somewhere around here. Okay, and as we added base to it, so let's see, we're going to be adding NaOH. NaOH is a strong base with a single hydroxide. It makes the math a lot easier. To a strong monoprotic acid. Let me start over here just a little bit further over this way. All right, so, and what you found was it almost went up like that, just like, almost seemed like a straight line where it was going up. Remember that? And that was the only range we were working with in that lab. Okay? So there's a lot missing from your understanding of behavior with this acid just from that. All that lab allowed you to do was to figure out, well, how strange it is that weak acids require so much more base to dilute them or to neutralize them. Okay? Well, what's missing from this is that this part down here where we got the really low pH, and what happens as you add more and more of the base, that's the part that's missing. Okay? We only looked at this section right in here. So if I were to keep adding, and this is pH over here, if I were to keep adding NaOH, if I started with a much stronger solution of this strong monoprotic acid, then I'd probably get a curve that looks something like this, if it's a strong monoprotic acid. The point where the number of hydrogen ions from the acid equals the number of hydroxide ions from the base is at this point here. Okay? And this point, this is about pH 7, is called the equivalence point. And it's also sometimes called the stoichiometric point. That's right there. So when we're doing stoichiometry, we needed to find what the limiting reactant was, because once the limiting reactant runs out, the reaction stops, and you're only reacting a stoichiometric equivalent amount of the two reactants. Well, this is the amount of base right here added to the acid, okay, This is the amount of base added to the acid that creates that endpoint for the reaction. The reaction doesn't happen, doesn't continue anymore at that point. Okay. Now, if we keep adding base to it, well, we're just basically we're just making it more basic, and so the pH just keeps going up. Okay. But as far as stoichiometry is concerned, this is the critical part. If we find out how much NaOH is added to the solution, and we know its concentration, and we will tomorrow know its concentration, then we'll have everything we need to do solution stoichiometry and find the concentration of the acid. Okay? Because we find out what the value of, or what the amount of NaOH put into the solution was at this point. Okay? That makes sense? We'll talk more in a minute about how we can figure out what that point is. That's the steepest point on the cliff face. That's the steepest part of the cliff face right there. Okay? So the curve keeps going, swinging upward until we get right there, and then starts to swing over. Okay? The point at which it stops swinging upward and starts swinging over. That's the equivalence point. That's the stoichiometric point. That's the titration end point most of the time. We won't end it tomorrow, but most of the time when you're doing titration, that's where you end. Okay? So this is for a strong monoprotic acid. Now, for a weak monoprotic acid like we did in our previous lab, and this is for, could be acetic acid. That's what we used it for. And we started about pH 2.4, and you found that it took a whole lot of base before finally you got it to the point where we had a pH of 7. Remember that? That's what we looked at in the last lab. That's the behavior you examined in the last lab. Well, the part of this you don't see is this starting point over here and the ending point. Okay? So this region in here, where we kept adding base and adding base and adding base, and the pH never seemed to change until finally suddenly it was just changing all kind of crazy. It just went, wow, way up, went jump way up. This is this resistance to pH in here is what we call buffering. Okay, that's the buffering region. The equivalence point is above 7. It's not at 7. It's somewhere above 7. So the point at which is a stoichiometric equal amount of hydrogen ions and hydroxide ions for this acid is not at 7. 7 is where we neutralized it, but the equivalence or stoichiometric point is not at 7. Okay? But this is the stoichiometric or equivalence point here for this acid. So the equivalence point will not always be at 7. It's almost always at 7 for strong acids for the first proton, but it may not always be there for other kinds of acids, for any kind of weak acid. Okay? So that's a weak monoprotic acid, or what we generally expect its behavior to be. Now the slope may be steeper, may be shallower sometimes, but the general pattern is the same for weak monoprotic acids. Everybody understand? Okay. Let's look at sulfuric acid because it's our only strong diprotic acid. So, since sulfuric acid is a strong acid, then we're not going to have that buffering region for the first hydrogen because it's a strong hydrogen removal, okay? And the first hydrogen you remove, whether it's strong or weak, the first hydrogen you remove is always easier. It requires the Ka value is much lower. The actually, I guess it's higher. Yeah. It's the first hydrogen that's removed is always going to be down here because it's easier to remove it. The amount of NaOH you need, or the base you need to remove the first hydrogen's always far less. So for the like sulfuric acid, we're going to have it look just like our strong monoprotic acid in the beginning. Okay? But there's going to be another equivalence point. There's going to be another cliff face up here. So what's going to happen is we're going to go over like that and have another cliff face up here. Okay? So because sulfuric acid has two hydrogens that can be removed, that are removed, two deproteinization series that happen at different times, okay, at different pHs, we're going to have two different equivalence points. Okay? So the first equivalence point is going to be pretty close to 7, and the second one's going to be somewhere up here. So the stoichiometric, you actually have two possible stoichiometric points. Two possible equivalence points that you can do the stoichiometry or titration stoichiometry with. But the first one is almost always the most practical one to use. Okay, it's almost always easier to use the first equivalence point. Okay, so you want to find this amount of NaOH used to find the concentration of the acid. So this is the equivalence point. Here, equivalence point or stoichiometric point, and this is also an equivalence or stoichiometric point. But this first one's the one that's almost always the easiest one to use. So this whole region in here is where sulfuric acid is reacting with the base but only one hydrogen is coming off. Okay, so that hydrogen is joining up with the OH. We're making water here. And what we have left then is a sodium ion and a bisulfite ion. I'm going to write it as one formula here. Even though in solution the sodium is separate from the bisulfite. Okay. Then up here, this second hydrogen is coming off. So up here what we have is HSO4 negative. That's the sulfuric acid minus one hydrogen. That's reacting with the base. Both these are aqueous. And now we've got sodium sulfate, which really in solution, if you understand the theory from when we were talking about all this in the beginning, we're talking about net and complete ionic equations, there's actually two sodium ions separately floating around in the water that are solvated, and one sulfate ion separately, or bunches of them actually, that are floating around and solvated in the water. And we also have water molecules that are formed from this reaction. So this reaction is what's happening actually not just here, but in this whole region here. Okay? And this is happening in this whole region here. And there's actually some overlap, but don't sweat that too much. Okay? So we actually have two equivalence points and two Kas. Okay, we have two acid ionization constants. All right? Wait. Okay? Okay? So if I were working with an acid like this, and I really, really, really wanted to know if it had 3 or 4 or 5 cliff faces, I'd take my time with it. I'd be all day long. Now tomorrow in our lab, we don't have all day long. Okay? We have an hour and a half. So it's quite possible that you'll be given an acid that's triprotic and you won't be able to find that last proton. It won't be evident. Okay? So it takes a little bit of patience and it takes a little bit of thought in how you're doing it about when you can add a lot of base. Because you know you can add a lot of base in these buffering regions, but when that pH starts to turn up, you got to slow down because that equivalence point is really important in there. Okay? And the same here. And you may not find that last point, but here's the thing. You cannot claim you have a weak diprotic acid unless you've eliminated the possibility that a 3rd or 4th proton exists up here. And unless you're really, really good tomorrow, you're not going to find it. Okay? So be careful in your claims. Got it? You might have what looks like in your titration, in your curves tomorrow, what looks like a diprotic acid, but it's a triprotic acid. Just be careful not to claim something when, you know, it might be triprotic. You got to say so. Okay? Everybody understand? All right. So you're going to be working with it a lot faster than you would if you were in a crime scene lab. Because in a crime scene lab, you take more time with it. We're going to be getting this done in an hour and a half. Some of you are going to take that whole hour and a half. And the noise from the way that we do it is going to be so great that you won't be able to see the last peak there, or last equivalence point, the last cliff face. It'll just disappear in the noise in the system. Okay? Now there is a way to do it. We have the lab equipment allow us to do it, but it just takes too much time for doing it on one lab period. Now, how many of you are taking calculus right now? Y'all look around. Look at these people taking calculus. Those are your go-to people. Okay? Because as part of this lab, you'll be doing first and second derivatives. And they're the people that know what they are. Okay? Here's the question, those of you who are taking calculus. This curve starts to sweep up and then over. So what does the first derivative look like at this point?
Oh, Lord.
I'm about to send an email to your calculus teacher.
No, hold on, wait. Okay, so that's the point of inflection. So
Yep, point of inflection, good.
the point of inflection of a first derivative graph
Yep.
would be a max or a min.
Yep, it'll be a
On the
peak.
first derivative graph.
It'll be a peak.
Okay.
Okay? And what does the second derivative look like at the point of inflection?
It will be a 0. It will be on the x-axis.
Okay, well it won't on the hours, but that's fine. I get your
Yeah,
point. What it does is the second derivative sweeps up and there's a complete break. And then it sweep over again. Okay? So it's actually using the second derivative is the best way to identify with quantitative accuracy what the inflection point is. But the noise in our graph probably won't make it so easy. I want you to do it just to see it. But if we were really, really careful, like I said, spending all day on a titration, doing it a little bit at a time, we could very clearly see that point of inflection. But it may not be so easy to see in our lab tomorrow. Okay? But I want you to do it anyway. Now, you're going to have 6 different acids, and every lab group works with a different acid. When you're done, your group will have to have a graph that just shows what this titration looks like. Then you need a graph that shows first derivative and a graph that shows second derivative. Okay? So your lab group is going to need 3 graphs for your work. In addition, you're going to need a copy of everybody else's unanalyzed graph without the first and second derivatives. Okay, so captains are going to be responsible for posting on a common page a copy of your unanalyzed graph so that they can look at that. So you can make smaller copies on your report and you can compare. Okay, my graph Our lab group appears to have been analyzing a weak diprotic acid, and group 1 was doing a strong monoprotic acid, and group 2 was doing so forth. Okay? That makes sense? Now, so you're going to be identifying what each of these graphs represent. All right, what kind of acids they appear to be. But you only have to do the titration stoichiometry for your lab group. So if this is the equivalence or stoichiometric point, then we would find out how much NaOH there is used at this point. Okay? And from that, because we're going to also know what the NaOH solution is, it's probably going to be a 0.10 molar solution, but I'll double check that before I turn you loose tomorrow, okay? So you'll find out what this is, you know its concentration, and we'll do the titration stoichiometry to find out the concentration of your acid. Everybody understand? So you got 2 goals tomorrow. Identifying the type of acid by strong, weak, monoprotic, diprotic, triprotic, and so forth. And also finding the concentration of your acid. Everybody understand? Anybody have any questions about what your goals for this lab tomorrow are about? Okay. Couple of points then. These are idealized graphs. Sometimes this plateau looks like a plateau, and sometimes it's like a pretty steep slope. So just because it doesn't look kind of like it's almost flattening out doesn't mean it's not, doesn't have a deprotonization or a buffering region going on there. Okay? So there's some judgment you got to make about these things. Okay? Don't whine and cry. Make your best judgment. That's reasonable answers to the questions. Okay? Got it? Discuss it with your people, other folks in your lab group. You can discuss it with other people if you want to, but you're not allowed to walk around the lab during the lab. It's too dangerous to be working with these kind of acids and bases. People just be walking around wherever. Okay? If you have a question for another lab group, only your captain leaves your group. Got it? Any questions? Safety first. Any questions at all? No? How many of you started on your procedures? A few of you. Okay. Some of you have a lot of work to do tonight. Guys, do not over summarize these procedures. Okay? These are very important procedures. And if you mess it up, you know, your results are not going to be good. Okay? So make sure you're prepared for the lab. Okay? Make sure you're wearing all your safety gear. All the time. Be careful. Any questions? One of the nice things about solution or acid-base stoichiometry is the ratio of acid to base is always 1:1. Okay? Let's go back and look at our strong diprotic acid here. If you're going to be examining and using this amount of base to start your stoichiometry, at this point, there's only 1 hydrogen being removed. And so the ratio between acid and base is always 1:1. Does that make sense? Now you still have to show me the balanced equation. All right? You got to show me why it's 1:1. Okay? But it will be one. That makes the molar ratio step pretty easy, because it's always going to be 1:1 if you've done it right. Okay. But you still have to be able to calculate do the solution stoichiometry, titration stoichiometry that we worked on in the last unit. So what do you say we practice just to make sure we're on the same page here? Okay. All right. So if 125.0 milliliters of a strong monoprotic acid is analyzed by titration with a 0.1 molar solution of sodium hydroxide, and the equivalence point is reached with a volume of 54.0 milliliters of that base, what is the concentration of the acid? So solve the problem yourself, or attempt to anyway, and then when you're done you can check your work. Pause the video now and you'll come back after you solve it for yourself and see how you did. So here's the correct solution. We've got a reaction between sodium hydroxide and hydrochloric acid, and it's a double replacement reaction, an acid-base reaction. So the sodium is going to join up with the chloride, the hydroxide is joining up with the hydrogen from the acid, making water. And here is the stoichiometry, the solution or titration stoichiometry, 54 milliliters of NaOH. You always start with the volume, at least I tell my students, always start with the volume of the solution whose concentration you know. You start with the volume of the solution whose concentration you know. And that would mean you are starting with the volume of the titrant. The titrant is the chemical whose concentration you know that you're adding to some other chemical to find the concentration of the second chemical. So you start with the solution whose concentration you know, use the molar concentration and the relationship between milliliters and liters to get to moles of the acid. Now you can't cancel milliliters with liters, so you have to have this ratio. This ratio requires that you also have this equality statement. In my classes, I require students to write down equality statements to justify any conversion unit, not conversion ratios from a balanced equation. That's what this is. This is a molar ratio. It comes from this balanced equation here. We've got 1 mole, an implied 1 here in front of the hydrochloric acid of the acid. I put down HCl. I think the problem just said any strong monoprotic acid. I could have put HA and Na capital A here. But anyway, we have a 1-to-1 ratio between this and this when the equation is balanced. And so you're always going to have that. With acids and bases, you're almost always looking at the first hydrogen that's removed at that equivalence point on your pH curve or in your titration system. And so you always have a 1-to-1 ratio if you know what you're doing. I make students show me they know what they're doing, because I always tell them, I'm from Missouri, because that's the show me state. I'm not really from Missouri, but I say that. Anyway, so then we're going to take that moles of HA and put it over the volume of the original volume of the acid solution. Again, we need it in moles per liter, so we've got to convert from liters to milliliters, and we get this value. All right, so in this unit we've looked at 3 different definitions or theories behind what an acid and a base are. Arrhenius, Bronsted-Lowry, and Lewis. We said that you don't have to do any real math with Lewis, you just have to understand the basic theory behind Lewis. But Bronsted-Lowry is pretty important, and so we do a lot of stuff with Bronsted-Lowry. We've done a titration lab now, and in the previous unit we were working with titration stoichiometry. We've been doing stoichiometry for like this will be the 4th unit where we've been working with stoichiometry. So stoichiometry is pretty big in chemistry. What I want to do now is to kind of give you one big problem that takes into account just about everything we've covered as far as big concepts. Okay, so it'll be one problem that'll deal with some theory. It'll deal with some math, a couple different kinds of math. So just hang on here and let me give you a problem that you'll have to work through. That's what we're going to spend most of our class period doing today, is practicing, and then tomorrow will be test review or preview, and then the test is on 2 days from now. Okay, so here's the problem we're doing. This graph represents a pH curve produced from titrating 50.0 milliliters of an unknown acid of unknown concentration with a 0.0750 molar KOH. And it asks you to find the molar concentration of the acid, and the molar concentration of the hydrogen ion, the molar concentration of the hydronium ion of the acid before titration. The molar concentration you're going to find also of the hydroxide ions before titration, the pH and POH before titration, and then using this graph, determine the general type of acid. Is it strong or weak, monoprotic, diprotic, or triprotic? So, let's go through this one piece at a time. We're going to do the titration stoichiometry first to find the concentration of the acid prior to titration. That is the original acid. That's what we're looking for here. All right, so we're going to start with the solution whose concentration and volume we know, and that's always the titrant. Okay, you always end up, when you're doing the stoichiometry, at the end of that problem, you're ending up with the concentration of the analyte, in this case the acid. All right, solving this problem then, we need to start with the volume of base solution, in this case potassium hydroxide, that was used to fully titrate the acid up to the equivalence point. Then we're going to use the concentration. Concentration of the base was 0.750 molar, which is moles of KOH over liters of solution. And since milliliters cannot be canceled by liters, we need a ratio of 1 liter over 1,000 milliliters, and so we have to have an equality statement that shows that. Okay? Now then, we have we're at moles of KOH solution. We need to get to moles of the acid. Since we don't know the formula for the acid, we can write a general equation for the dilution, or the reaction between the acid and the base, based on what we know about the acid. Let's go back to our graph here. So looking at this graph, this is pretty clearly a diprotic acid, and it's a diprotic weak acid, which is going to this question down here. We'll get to that in a minute. But if we have a diprotic acid and we don't know what the acid formula is, here's what we do know about diprotic acids. They have 2 hydrogens, right? So if I write out an equation, I'll write out H2A, okay? Because that A then stands for any kind of anion. In this case, it'll have a 2 negative charge to accommodate the 2 hydrogen ions. So this is an aqueous acid, or we're going to assume that it is. Actually, you'll find out later on in AP chemistry or college chemistry, this particular acid probably will be listed as a solid and not an aqueous, but that's something that we'll worry about at a later time. All right, so then we're going to react that with KOH, and we know that KOH is soluble because all group 1 metal salts are soluble. And so the hydrogen is going to join up with the OH, or one of the hydrogens is going to join up with the OH. We're going to get water. And then we'll have the potassium with the one hydrogen that's left. Let me write this out this way. When I take the 1 hydrogen off here to make 1 water, what we have is HA1 negative. Okay, the way we had H2A was to have an anion with a 2 negative. So if we got 1 hydrogen on there, this actually comes out to be HA. Okay, and then the potassium has a 1 plus charge. So we put those together, and we're going to get KHA. We're going to assume that to be aqueous. We really don't have information to tell us otherwise. Okay. All right, now, so this is a 1-to-1 ratio, and it turns out that when you're doing titration, all of these things are always going to be a 1-to-1 ratio because you're removing 1 hydrogen at a time. If we go back to our pH curve here, there's 1 hydrogen being removed in this region here. There's a 2nd hydrogen being removed in this region up here. Okay, so you have to keep those separate.
When you're looking at that graph, how can you tell if that's strong or weak?
Well, if it was strong, we wouldn't have this buffering region. You wouldn't have this sort of plateau right here. It would be sweeping up from the bottom in an easy curve. That'd be strong. So a strong diprotic acid is only strong for the first hydrogen being removed, and that's in this region here. And it's always weak in the second region. So the second region has that plateau. Okay? Well, there's a plateau here. Since there's a plateau here, that means that first hydrogen is also a weak acid, or that first hydrogen being removed is a weak acid, okay? So now back to this. So our ratio of KOH to the acid is a 1-to-1 ratio. And so now we can write a molar ratio for that. We want the KOH on the bottom here, 1 mole. Now you could argue, well, it's a 1-to-1 ratio all the time. Why do I need a balanced equation? The answer is I told you so. Okay, I know that's kind of cruel and all that, but come on. I want you to write it out. It helps to emphasize and make it clear that's what you're doing. All right, if you don't write it out, I don't really know that you know what you're doing. Okay, so where am I from? Missouri. Okay, and so our acid is 1. That sounded pretty tired, like you weren't happy to tell me I'm from Missouri. I'm sad now. Okay, moles of KOH cancel. We have moles of H2A. We need to find the molar concentration, so we need a volume on the bottom. Molarity, or molar concentration, is moles of solute over liters of solution. So a molar concentration of our acid, and when we put the symbol for anything inside brackets like that, that is a symbol that means the molar concentration of what's inside. So the molar concentration of this acid then is going to be the moles of H2A over liters of H2A solution. Okay? Well, the volume of H2A solution that was listed in the problem is the 50 liters that I originally put in here. It's actually over here, 50.0 milliliters of H2A solution. We're going to put that on the bottom. We have to convert milliliters to liters to get liters of solution on the bottom. Well, I've already got this equality statement here. I don't have to write it a second time. So I'm going to build a conversion unit then where we have 1,000 milliliters on the top and a liter on the bottom. That will cancel out milliliters. And we now have moles of H2A over liters of H2A solution. That doesn't much look like an A here. Let's try to make it look more like an A. And now we're ready to do the math. So I've got the 50 milliliters of the acid solution on the bottom, because what I want in the end is moles of solute over liters of solution. The only way to get liters of solution on the bottom is if I start out by putting the milliliters, because that's what I was given it. I was given it in milliliters. Now you could actually do a second math problem somewhere down here and write 50 milliliters of H2A solution on the top over 1 and basically flip this conversion unit and come up with liters and then plug that in here. That's fine, but why do 2 math problems? I like to do it as 1 problem, but you can do it as 2. You can do 3 or 4 or 5 problems if you want to, and then put them all together, as long as you put them all together in the correct way. I like to keep them all organized, neat in one long problem, because I can see what's going on better. But if it works for you better the other way, that's fine. All right, so we're going to take this 143 milliliters. Oh, it's 143.4. We're going to multiply that times 0.0750. And we're multiplying that times 1,000. And hit equals. Then we can divide the things on the bottom. So I'm dividing first by 1,000. Okay. And then I'm going to divide by the 50 here. So I notice I got an answer first and then divide again by 50.0. If you do divide twice, a lot of calculators won't understand what you mean by that. Okay. I mean, I'm sort of personifying a calculator. They don't have feelings, but the point is that that's the operation. Multiply everything across the top, then divide each of the things on the bottom separately. Okay? All right, so what we got now is 0.2151 moles of HA, or H2A, over liters of H2A solution. looking at the problem, I've got 4 significant digits here, 3 significant digits here. Remember, leading zeros are never significant. So that's 3 significant digits and 3 digits here that are significant. So I want 3 digits of my final answer. I need to round off this 1 at the end. I'm going to round that off to 0.215. And since moles of H2A over liters of H2A solution is molarity, I can just use the symbol for molar concentration. You don't have to. This is perfectly okay, but that's the way that you can do that, okay? Molar H2A solution. All right, so that's the concentration of the acid. All right, now, if the concentration of the acid is this, then the concentration of the hydrogen ion is also going to be this in that original solution, okay? So if the molar concentration of H2A is 0.215 molar. Since this is a weak acid, we know this is the molar concentration of the weak acid, okay? But because this is a weak acid, the molar concentration of H plus must be less than the molar concentration of the acid. Okay? So all that we can say for this about, if it was a strong acid, we could say that's the concentration of hydrogen ions, because a strong acid dissociates completely. But because the weak acid, we have to say that this must be less than that. That's all we can say. We can't say specifically what the concentration of H plus is. So all we can say is that the molar concentration of H plus is less than the molar concentration of H2A. Okay? Since the molar concentration of H plus is always equal to the molar concentration of H3O, and this is the way we represent acid strength or acid concentration with the Arrhenius system, the Arrhenius theory of acids. This is how we represent it for a Bronsted-Lowry. So, but those are always equal, because when you do the calculations, they end up being the same. So then we can say the molar concentration of H3O must be less also than the molar concentration of the acid. Okay? All right, that being the case, then we're going to be able to calculate pH and pOH, but we're going to have to say it's more than or less than. We can't say it's exactly that. All right? Because of weak acid. In a weak acid, you're never going to have as many hydrogen ions as you have acid units, acid moles, or acid molecules. Okay? It doesn't dissociate completely. So that's the best we can say. So for pH, that's the negative logarithm of the hydrogen ion concentration, or negative logarithm of the hydronium ion concentration. This is the way you'd represent it in Arrhenius. This is the way you represent it in Bronsted-Lowry. So we know that the pH then, because the more hydrogen ions you have, the lower the pH. You know that? That makes sense, right? Because stronger acids you've always thought of as having a lower pH. That's not true. You now know that strong acids are strong acids because they dissociate completely. That's a whole different way of thinking about acids than the way you were probably taught in earlier grades. All right, so we're going to first calculate it, but what we're going to know is the pH must actually be bigger than the negative logarithm of those values. Does that make sense? In this case, for weak acids, then the pH has to be larger than the negative logarithm of H plus. Okay? And pH is larger than the negative logarithm of the hydronium ion concentration. All right? So we don't know exactly what it's going to be. We can say, okay, we know it's less than 7 because it's an acid. and we know it's more than whatever we calculate. That makes sense? All right. So our concentration that we calculated was 0.215 molar. So we're going to say the pH is going to be greater than the negative logarithm of this 0.215. And let's see here. On this calculator, I'm going to do negative logarithm 0.215, and I get this number, 0.6675615401. When we're rounding for logarithms and exponents, when we're doing logarithms, we're going to take this original number and find how many digits we have past the decimal. That's how many digits we want in this answer. In this case, it'd be this many digits. So our rounded off answer is going to be a pH that is greater than 0.668. Okay? All right then. For the pOH, the simple equation is that 14.000, or as many zeros after the decimal as you want, is, yep, is pH plus pOH. Okay, so we can plug into that. pH we know is going to be actually greater than this, 0.668 plus pOH. Okay, and so we want to subtract this number from both sides. And so we can take 14.000 and subtract 0.668, and we get 13.332. So if the pH is going to be greater than this number, then the pOH has to be actually less than this number. Does that make sense? All right. So instead of this, what we really need is that. That makes sense? Everybody good? Because it's a weak acid. Got it? All right then. Last thing we got to calculate is the hydroxide ion concentration, right? All right. So there's a couple of ways to do this. We can calculate hydroxide ion concentration as the 10 to the negative pOH. Or we can use Kw, where the hydrogen ion concentration times the hydroxide ion concentration is equal to Kw. Using Bronsted-Lowry, it would be hydronium ion concentration times hydroxide ion concentration. In any event, Kw is 1.000 times 10 to the negative 14 molar squared. Okay? So let's do this first. Okay? So 10 to the negative 13.332, that's where we're going to start anyway. So let's see here. Here's 10. I'm going to put that in parentheses, and I'm going to say change the sign. Remember, there's two different negative buttons on your calculator. It's written different calculators have different kinds of labels for this button. You want whichever of these negatives is the change of sign. On this type calculator, this is the change of sign here. This is the subtraction button. Okay, so change the sign and 13.332, and that's going to give me this number, 4.65586 times 10 to the negative 14 molar concentration. All right, let's do the rounding then. In a logarithm, and that's what this number is, a logarithm, the significant digits are those past the decimal. So we want 3 significant digits in this answer. Okay? So we're going to round that then to 3 significant digits. And we get 4.66 times 10 to the negative 14 molar concentration of hydroxide ions. Now, again, it's a weak acid. All right? Got it? Right? All right. So the concentration of hydroxide is actually not going to be this actual number, but it's going to be more than this. All right? If your hydrogen ion concentration is less, because hydrogen ion concentration times hydroxide ion concentration has to equal the same number every time. So our hydrogen ion concentration, remember, where do we put that? The hydrogen ion concentration is actually less than the concentration of the acid. If the hydrogen ion concentration goes down, this one has to go up. So in reality, the molar concentration of hydroxide ions, this one has to be greater than 4.66 times 10 to the negative 14 molar concentration of hydroxide ions, because it's a weak acid. You following me? You understand? You understand about greater than and less than here? Okay. If you don't speak up and tell me, I can't help you, okay? You got to speak up and tell me something. All right, let's calculate it using this then. Then if we've got 1.000 times 10 to the negative 14 molar concentration equals hydrogen ion times hydroxide ion concentration. And the hydrogen ion concentration is actually less than this number. We're just going to put in that number to start with. 0.215 molar times the hydroxide ion molar concentration. Then we're going to divide both sides by this number. All right. This number cancels. Molar squared is canceled by molar. This is like molar to the first power, molar to the second power, and so you cancel one of the molars on the top. Okay? And we just do the math. All right, so let's go back to the computer generated calculator system here I've got. Now I'm going to start out by putting what's on the in order to keep the order of operations separate, because I really have one multiplication problem divided by another number. So to keep the multiplication problem with an exponent, for that matter, separate, I'm going to put this in parentheses. I'm going to say 1.000 times 10 to the negative 14. Well, I can use the double E button right here, because that means times 10 to some number. Use the change the sign button here and put in 14, and that's 1.000 times 10 to the negative 14. Okay, then I'm going to divide by 0.215, and I get this number. So 4.65116 times 10 to the negative 14 is the direct calculation for hydroxide ion. Okay. But we know this number actually has to be, this value actually has to be greater than that. Okay, so it's not really equals to, the hydroxide ion concentration has to be greater than that number. And now we can round it off. We could have rounded it off first, I guess. So let's see, going back to this, there's 3 significant digits here. That's what I want in my final answer. And I get 4.65 times 10 to the negative 14 molar concentration is equal to the molar concentration of hydrogen ions. Okay, I could have just left out molar because that means molar concentration. Okay, in that case, it'd be acceptable to leave out your units of measurement. However, just to be safe, always put your units of measurement on there when you got one. Okay, and that happens to be the same number as, almost the same number as that one, doesn't it? Slightly off. Okay, but pretty close. Any questions? So I bet you got all the numbers right, but the greater than and less than stuff you had trouble with, didn't you? Okay.
Will there be a question like that on the test?
I can't say there will or will not be a question like that on the test. I mean, basically you do all the math the same whether it's greater than or less than. And if it were me and I had a problem like this, I would then go through, after I do all the math, and change the equal signs at the end to greater than or less than. I'd mark them through like that and say it's greater than or less than. Actually, I should have kept this as less than here. Okay? Because if you know, listen, let's go back to the beginning here. If it's a weak acid, you know the concentration of acid is greater than the concentration of hydronium or greater than the hydrogen ion concentration because weak acids don't dissociate completely, right? If I were writing out an equation for that, then I would say H2O, or H2A rather, let's call it aqueous. If I'm dissociating in using the Arrhenius system, I would have to have a double arrow. Okay? That's a reversible reaction. This does not dissociate completely because at a certain, when I start dissociating these, some of these start reforming that, and eventually we reach a point where the rate of this dissociation is equal to this reformation or reassociation. That makes sense? Or writing it using the, this is an Arrhenius way of thinking about acids and bases. If I were doing it with Bronsted-Lowry, in Bronsted-Lowry, the definition of an acid is something that donates a proton to another chemical species. And so I have to have something for this hydrogen ion to go to. And so we're going to form H3O. And we'll have that double arrow again. Okay. In the actual reaction, the hydrogen ion is not going to a water molecule. Okay. In the actual reaction, the hydrogen ion is going to a hydroxide ion. Let's represent that here. In fact, let's do it with Arrhenius first. Okay. Here's Arrhenius, H2A. And we're going to be reacting that with KOH. All right. So the hydrogen ion is actually being removed and joining up with the hydroxide ion. So in that case, we would represent it like this. But since there's only one hydrogen being removed, the potassium is going to join up with the HA negative. Okay? I think I wrote that earlier, didn't I? Okay? Yeah, there's the reaction right there. Okay? So we got KHA for the first dissociation, for the first hydrogen that's removed. Okay? Now let's do it with, well actually, this would be the same reaction for Bronsted-Lowry or Arrhenius. Okay? The only difference is, the way that Arrhenius thinks about it, is that you think about this being dissociated already. So H2A is in a sense being reacted with K+. We're kind of like writing The original kind of chemical reactions we learned to write, chemical equations we learned to write with a sort of a modified system using complete ionic equations, where we write with the OH here. We separated the K and the OH. So the difference here is in the theory, where the hydrogen from the acid is actually going to go over and join up with that. Okay? So in this case, in the hydrogen, this is the base because the hydroxide came from KOH. KOH is the base because it accepts that hydrogen ion. Does that make sense? The reaction actually comes out the same. The equation actually comes out the same. All right? So the only equations that look different really are the dissociation equations. Okay, in Bronsted-Lowry, the hydrogen ion has to go to something else and join in a covalent bond, joining up with a pair of electrons the base already has for it. Okay? Then the base is defined as the species that accepts that hydrogen ion. That base has to have a pair of electrons to provide a covalent bond site for that hydrogen join up. Okay? So I built that question to cover a lot of territory. Alright? We covered just about all the theory, somewhat. We covered this whole unit and all the math.